Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, thank you for coming. It's my pleasure to introduce Dr. settingڳցöthe. He's currently a postdoc at the UIUC, and he got his PhD from Institute of Automation in Chinese Academy of Sciences. And today he will tell us his work in UIUC on the emotion sensing. Okay, Zheng.
I want to say thank you, Zheng, for to invite me to visit MSR. It's my great pleasure to be here, introduce my research. The topic of my talk today is machine understanding of audio and visual affective expressions. You're welcome to ask a question, and if you are watching my presentation online, if you have any questions and comments, please send an email to me. So this is the outline of my talk. First, I will introduce the motivation to answer the question why the research is important. And then I will give a brief description of the history of the affective recognition research. Then I will introduce the three studies we did about the audiovisual affective expression analysis. Then finally, I will give the summary and talk about challenges we have faced in this research. So emotion is an important element in human daily life. Some emotion will enrich the meaning of the communication. Some emotion will motivate the people action. So in our modern society, people spend more and more time to study and playing and working and even living in the computing world. So the affective recognition system provided a way to enable the computer to understand and express emotion and provide a way to build the affective support environment, the computing environment. So here I list some of the application. The one is the computer-aided learning system. I will talk a little bit detail, give example. So in the learning environment, a student is expected to experience a series of failure. So, but anyway, each people have a different threshold to tolerance the confusion and the failure. So if the computer can understand the change of the affective state of the student, so they can provide appropriate the tutoring strategy to help the student engage in this learning the procedure. Another application is customer service, specifically the call center, the machine call center. So if the machine can understand the affective states of the caller, they can respond appropriately, or even the pass the control to the human operator. Another is the intelligent automobile system. So right now, the several automobile companies investigate the possibility to build the system to detect the fatigue. So in order to monitor the vigilance of the driver, so in order to reduce the accident. The people right now spend more and more time in the online communication, like use the MSN, but the people mainly use the text to transmit the message. So affective recognition system to provide the possibility to build the affective bandwidth. So in this way, the affective recognition system can enrich the communication. Another application is the game and entertainment. For example, the Xbox. Because when people are playing the game, they involve a lot of emotion. So if the game system can detect the change of the players, like whether the player is bored, whether he's frustrated, whether he's interested. So the game system can adjust the gaming system, and help the player to engage this kind of the game. Another application is video indexing and the retrieval. So right now there are several websites which provide the way for the people to upload the videos in the website. So the affective recognition system provides a way to analyze the video. So categorize the videos in terms of the human affected states. For example, the comedy, the video, the tragedy video, scaring video, exciting video. So this can help the user to search the video according to their preference. Another is electronic customer relationship marketing. So we believe the affective recognition system can help the company to get the feedback about the preference, the attitude of the user to the specific the product or the advertisement or the service. So that's help the company to survive in the competitive environment. So another important application of affective recognition research is in the affective-related research in the social science, like psychology, psychiatry, and education. Especially, we notice more and more people are engaged exploring the mystery of emotion in our daily life, because emotion plays an important role in the human creative and the perception, memory, decision making, and health. So here I give an example of the human affect recognition can be used in the computer-aided learning system. This is a prototype of multimodal human-computer system, which was built in a NASF ITR project. Well, I was privileged to participate and working with interdisciplinary team from the engineering and the psychology. So you can download the video in the ITR website. So in this environment, the student is sitting in front of the computer avatar. And in this environment, there's no keyboard, no mouse, but just a lot of the camera and the microphone. So specifically, this camera is used to track the facial expression, to analyze the emotional state of the student. And there are a set of the infrared camera to monitor the eye movement, to infer the engagement of the student. And there is one camera is used to monitor the task state, and the microphone to detect the keyword, the microphone to detect the keyword of the subject, the speech. So this is the task state. And then, so based on all the information from the multiple sensors, and then, so the computer avatar can make appropriate the tutoring, for example, the encouragement and guidance and the transition. So this is so this is an example of the affective recognition system can be used to improve the student performance, help them to engage this learning, and in the long term, help them to build interest for the science and the math. So, do you have any question? Okay, so then we'll talk about the history of the affective recognition research, which is based on our recent the survey. I wrote with Mario Pantic and Glenn Roisman and Tom Huang. We're working together make this a comprehensive the survey. So here I just used the one slide because of a time constraint. I just used the one slide to give the whole picture and the history of the affective recognition research. So actually, the affective recognition research started 3 decades ago. The William and Stephen in 1972 who did the initial efforts to use the computer to analyze the affective recognition, affective expression, focus on the audio expressions. In 1978, the Suwa and his team, research team, did early work in the facial expression analysis. So then we noticed that there were significantly increasing number of the efforts toward this kind of the affective expression recognition, focus on the unimodal, the methods. So in 1998, a study was conducted in our group by the Larry Chen and Professor Tom Huang. They did early the work of the audiovisual, the display, the analysis about the facial expression. So in 2002, before the 2002, most of the efforts are focused on the post emotion. That means the data was collected, asked the subject to pose their expression in front of the camera or the microphone. So in 2002, there is a study was investigated the spontaneous displays, focused on the audio expression. In 2004, well, we noticed that there is a study focused on the vision-based spontaneous displays conducted by Jeffrey Cohn and his research team. They investigate the difference between the post facial expression and the spontaneous facial expression. And in the same year, we did work to study the audiovisual, the non-basic emotion, because most of research are focused on the basic emotion, or called the prototype emotion expression, including the happy, sad, fear, anger, disgust, and surprise. But we noticed there is some cognitive and motivative states are very important of human-computer interaction. For example, the interesting, the boredom, the frustration, and the puzzle. So we did a study to analyze this non-basic emotion for HCI. And in 2005, we noticed that there is the study who investigated the audiovisual spontaneous displays based on the data collected in the human-computer interaction. Actually, it's a Wizard of Oz scenario. So in 2006, we did a spontaneous expression analysis using the data collected by the psychological the study called adult attachment interview. This is based on the human-to-human interview. In this field, the most of existing studies are focused on the unimodal. Image process is limited to the facial expression or the audio prosody expression. Okay.
Could you say again what spontaneous?
Oh, spontaneous is a different. We can call this the real emotion expression. In other words, because right now we did this study. We first focused on because the emotion data is very difficult to collect it because it's very subtle and very short. So the people started this research just to active
Okay.
stager, ask people to.
I have another question. I had heard that Ross Picard and Media Lab people had been doing a lot of motion stuff like in the 90s or something. Where does that fit in? Do you know?
So which app?
Media Lab,
In the
MIT.
MIT. Oh yes.
Ross Picard, and
Oh yeah. Sure. They rewrote a significant book about the affective computing. Yes, they did some. She and her research team focused on the first. They started the work focused on the physiological the expression. So, but anyway, in our survey paper, we also cited heard the paper in this field. So they also did some research about the facial expression, and he did some very interesting work about how to use the multimodal. For example, the facial expression and the posture and the physiological responses that combine together to build the system to recognize the expressions.
Probably I can fill you on that. I was the one who was doing it.
oh, okay. I only sort of peripherally know about it.
Yeah. So basically, we are looking much more than audio. We were looking at much more than audio and video, and we were also looking in certain contexts. So most of these studies are in general context, right? But if you're looking at a context when you are looking at a student who's trying to solve a problem versus a driver who's sort of driving and there is stress, so those kind of emotion recognition applications were much more focused on a certain context. But they did incorporate like sometimes audio, sometimes video, and often the direction was to incorporate multiple modalities.
Yes, this is very good discussing. So we noticed that the context is very important for the emotion recognition because the emotion is related to the situation, the human experience or imagine. So if without the context, we won't misunderstand the expression. So especially sometimes the people judge the expression is full of the ambiguity. So the context is a constraint to accurate judgment about the expression. So I focused my efforts on the audiovisual expression and the spontaneous displays in this field. And this also we did the survey. Also noticed that there is two trends. Here, one trend is more and more people shifted the efforts from the posed expression to the spontaneous expression, and from the unimodal analysis to the multimodal analysis. Even the visual-based analysis, people is exploring the integration of the facial expression and the body gesture and head movement. So the audio-based the analysis, people also explore the integration of the linguistic and the paralinguistic to improve the performance of recognition of affective behavior. So we move to the next section, which Well, I will talk about our efforts in this field. The first I want to talk about is multi-stream fused HMM for audiovisual affective expression recognition. Why we focus on efforts on the audiovisual expression, we can explain from the psychology perspective and engineering perspective. From the psychology perspective, a lot of studies demonstrate the importance of the integration of information from the affective-related modality to get the coherent interpretation and judgment of emotions. Because the emotion judgment is a ear-post problem. Actually, the emotion include, generally speaking, the emotion include the 5 elements. One is behavior, another nodal behavior. Another is the counter appraisal and action tendency and physiological responses and subject feeling. So actually, a lot of for example, the action tendency, the subject feeling, and the cognitive appraisal, we can get any information from in our communication. So we most of the time we judge the emotion just based on the behavior, especially audiovisual expression. So from the engineering perspective, the multimodal fusion provide a way to make use of the comprehensive information from the different modality and reduce the limitation of the technical. For example, the image processing sensitive to the illumination and the pose, the change, and the occlusion. The speech analysis is sensitive to the noise. So combined audiovisual modalities, it's provided the possibility to reduce the limitation of technology. I studied this research on the data collected in our group, which is collected by Larry Chen and Professor Tom Huang. They collected data, asked the subject to pose the 11 affective states, including the 7 basic emotion states, and 4 cognitive states. As I mentioned before, interest, the boredom, frustration, the puzzle, because we believe that it's a cognitive and motivative state. It's very important for the human-computer interaction. In our experiment, we used 20 subjects, 10 male and 10 females, and each subject asked to express the audiovisual expression 3 times. So the first step of the affective recognition is a feature extraction. We use the 3D face tracker, was developed by the Tao and Huang in 1999, called the piecewise Bayesian volume deformation tracker to track the 12 facial motion units around the mouth, eyes, eyebrows, and cheeks. So this is the picture of a 3D face tracker. For the audio part, we used because there is a lot of study indicated the correlation of the prosody and emotion state. So in our study, we used the pitch analyzer, the formant, and the full bandwidth as the audio feature. So the first experiment we did is we try to, in this kind of the classification task, what feature are most important, what feature contributes the most in this kind of a task. So we use the backward feature and selection and the forward feature selection to analyze the contribution of the different the features in this classification task. So here this is this experimental result. The x-axis represented the feature number. From the 1 to 12 is represented the 12 motion units, the facial motion unit. From the 13 to the 24 represent the derivative of this 12 facial motion units. The y-axis is a frequency. That means the number of occurrences in the feature selected subset. So the feature with the higher frequency means they contributed more in this classification, the task. So in our experiment, especially the backward feature selection and the forward feature selection, we noticed the action units 7 and 8 represented the brow movement contributed the most in this classification task. The feature around the mouth contributed less because these features are related both of the speech content and emotional state.
So the total number of facial expression facial action units is more than 24, right? It's more than 25. So
Just
it's just like a part of.
no, it's a 24, but the just this shows the 25. Wait, but actually it's 24. It's from the 1 to the 24. So.
Okay, so basically it's 24.
24.
But there are more than those, right?
No, just we use the 24 to put the 24 feature.
Text, right? Yeah, different. This is just those vectors.
Yeah.
It's
So the number, just the
not related to
the feature number.
Psychological effects. Like here, talking about facial action units.
I thought you used facial action units.
Mm-hmm. Oh, it's not a feature actually. It's a motion units. It's
It's
oh yeah.
units, okay.
Yeah, it's defined by our system. It's a
Okay,
different
facial
from.
action units,
Oh, yeah, different of facial action unit developed by the Paul Ekman, right? So you mean. So for the audio feature selection, we use the picture manager and the format and the bandwidth, and they are corresponding derivative to do this kind of feature selection experiment. Our experiment show the picture and the manager contributed the most in the audio expression recognition. So the most important for the audiovisual expression recognition is how to integrate the information from these different modalities to get the better performance. So, for example, suppose we have a 3 string of the feature, or 3 string of signals. So for this sequence, we can use the HM model to model them independently. So most of the methods right now people use the first is each streams are modeled independently, and then the output of each modalities of the different modalities are combined at the end. So they put together to integrate. But we call the multi-stream independent HMM. It's so when they build the component HMM, they don't care the observation of the other streams. So it's so actually they lose the dependence of the different streams. So our efforts is to try to build a model to make use of the correlation of the different streams. So we proposed the multi-stream fused HMM. So this theoretically, this is based on this equation. This equation is according to the maximum entropy principle. The basic idea is so right now our purpose is to try to estimate the joint probability of all the observation of the different string. So if we have a difficulty to calculate them, because you know that the different string have the different time scale, different metric level, even the put together maybe it's a high dimensionality, the space, so we can use the approximate method. So in this equation we the joint probability of the observation is approximated by the first term is the product of the probability of the component of the different streams, and then the second term is to try to to categorize the correlation among the different streams. If we delete this second term, actually this is decision level diffusion. This is this kind of thing. So we model it independently and combined at the end. So we use the second term, try to categorize the correlation among the different streams. So the W is how to choose the W. There's two criteria. One is W should reflect the correlation among the different streams. Another criteria, so that means that they can categorize the correlation. Another criteria is should be easy to calculate in the original joint probability. So these are two criteria to choose the W. So in our task, the W have two choices. The W we can choose the W equals O, and or choose the hidden state if we model the streams by HMM model. So the different choice, we can get a different representation of the multimodal fusion problem. So if we choose the W, all the W equals O, so that will become the original problem. So estimate the joint probability. If we choose the W, all the W are the hidden state, so that means that we try to use the correlation among the hidden states of the different string. That basically it's become the couple HMM. Couple HMM just try to model the correlation of the hidden states. So my choice is between them. We choose the, for example, for the stream 1, we choose the W1 equals the hidden state, and the other W are the observation. So that means we try to calculate the correlation, make use the correlation of the hidden state of one string and the observation of the other string. So we try to use the coupled parameter of the hidden state of one string and the observation of other string. So we can argue that in this way, it's much better than the coupled HMM model because based on the maximum the mutual information, we notice if we use for example, we use the U, and the other use the observation. This we can get the mutual information of better mutual information than if we choose the W. All the W are hidden state. So this is the basic idea of the fused HMM. So when build the model of the component HMM, we always make use of the couple the correlation of this hidden state and others the observation of the other strings. So do you have any question? Okay.
So here you assume that, for example, you assume O1, W1 is equal to U11, is that what you mean?
So okay, so let's
right, so O1 is equal to U11, right? And then W1 is equal to O1, but W2 through Wn are equal to O O's, right?
Mm-hmm.
So that means the denominator and the nominator, and the left-hand side, the POs will be cancelled for I from 2 to n, right?
Okay, let's have the two hidden the slides. I think I can show you. Maybe this is the more. Okay, so for example, we try to build the component HMN for the I component HMN. So we use the W, J, when J is equal I, we choose the U, hidden state. And the other J not equal to I, we choose the O. So we can, the diffuse model, we get this equation. So for example, we can put all of them into the equation. So this is a U, other is O, right? This is a U, this is other O. So we can get this equation. So we can delete it, right? And so someone deleted the POI is still there. And the other one, so for example, O1, we can delete it, right? O2 or ON, we can delete it. So we can get this equation. So that means the first, this joint probability, we can approximate the first is PO, and another second term is given the UI, what kind of a probability of the O of the other streams. We can get this equation.
So how do you decide the N? Because for certain period, the ON amount depends on the previous observations, right? So, for example, if it's one order Markov chain, and
you mean the N?
Yeah, you have the N out there, and you cannot just take all the history, right?
N is the number of chains.
In the streams, not the modality.
Yeah. So actually the
Each one of those O's is a sequence, right?
actually it's sequence. So okay, I can give you the learning algorithm. It's very simple. It's helpful to explain this this algorithm. So the learning algorithm, we should first build the component HMN are trained independently by EM algorithm, and then we infer the hidden state, the best hidden state, using the virtual bit algorithm, and then we calculate the coupling parameters between the N HMN are estimated by this one, because so that means the given the state, what is the observation of the O? So it's kind of straightforward. So O is here. Also did some, okay. Right now okay, that's the, so we try to estimate this joint probability. We make this choice, so we can get the approximation. The approximation is first the probability of independent the stream. And then the second term is given the U, the hidden state of I stream, and what kind of probability of the other observation. So this we also make a little simplified. So because this one we use the conditional independence, so we simplified to here. And then so finally we get this equation. So the joint probability can be estimated by PO and the product of the conditional probability. So
here is still what a hypothesis means. You should look at equation 7, right? And the P is a P hat I of O's. So that has nothing to do with U, right? U is not in the picture. But now on your right hand side, you put a U there. So that's something I don't feel comfortable about this equation.
So you mean from here to the last
from the top, the
from
PIs. Yeah, the PI. I don't see where the U comes in.
So okay, so
Right. So PIs. I mean, it's very clear. Just like get the output. What's likely of that output? Right? You don't know the state yet, right? But now all of a sudden on the right, you put a UI there. So that's.
Oh, okay. Actually, this is the P. Okay, you mean the PI, right? So actually, it's a
condition UI. Yeah.
condition UI, right?
So I mean, on the other hand side, there's no UI there. Right? It's not independent of UI. But on the right hand side, you have UI.
Oh, okay. So this UI. So here it's for example we use this UI here. Oh, sorry. So you mean so right now we choose the string, the W, we choose the UI. So there's no question here, right? You have your question here. It's how to get the UI, right?
No, here, over here. Sorry. Over here, there's no UI. It's not here, right? I mean, this quantity is not related to UI. Right? My understanding is that
This
UI.
It's UI is actually implicitly included this. It's exactly this. It's implicitly included this equation because if you calculate this the joint probability, you must because you use the hidden Markov model. So this is UI here. You must estimate, right?
Only marginalize over UIs. There are many UIs. There are many possibilities of UIs. UI is hidden very.
Okay. This is the algorithm. So you see, right now we independently to train the HM model for each string, right? So we get the best hidden state of sequence UI of the component HM. So we pick up the UI. This is the best estimate of the hidden state. So. So, okay. Mm-hmm.
Yeah, you should have mentioned this before the equation 7.
He did have UI as a function. He did have the
Okay, thank you. I understand. Okay.
Thank you. Yeah. So, okay, here's our experiment result. We did the personal independent experiment, used the leave one subject out the cross-validation methods. And so we have, we choose the three strings and build the three-component HM model. One is a visual HM model, which is made up of the 12 facial motion units. And another the pitch HM and the energy HM. So we have the three component HM. So we combine them. One is use the multi-strain independent HM model, which is based on the independence of the different strains. Another is a multi-strain fused HM model. So we also investigated the performance at a different level of noise. So
what's the recognition accuracy on?
What?
The accuracy is on
Accuracy.
classes and
Accuracy is how the.
how many classes are there?
Okay. It's 11 classes. Mm-hmm. So we artificially added the white noise in the audio channel. So you will see the pitch HM and the energy HM, the performance decreased with the decrease of the SNR dB from the 25 dB to the 0 dB. So the pitch and energy, the HM is decreased. The visual HM keep constant because we just added the noise in the audio channel. So the independent HM model, it's most of the time get the better performance in the unit, the string, the component HM model. But when the signal noise ratio is lower than the 5 dB, it's worse. It get the worst performance than the visual HM model. But the fused HM model has the best performance. It's always better than the unit string and the independent HM model.
So I don't understand here in the independent HMM, why is the fused one is worse than individual one?
Because actually the when the individual streams very worse, this the combination also take a risk. Because for example, if the one component is much higher, but another stream is another component is much lower, you combine together, maybe because that you can get a compromise and you get the middle. So this is a take risk. So
Yeah,
this is
but-
the possible.
Yeah, but if I choose the weight optimally,
Oh,
I ignore.
okay.
I can ignore all the.
Okay, yeah. This is a,
It seems not logical that I get worse result than the.
oh yeah. So if you can monitor, you can robust estimate the reliability of different string. You can adjust the weight, not to get the better performance.
So what weight
but-
do you choose here?
We choose here the weight is just proportional to the accuracy of the string of the component streams. So
So in HM, it's just not simple multiplication of likelihoods. It's weighted multiplication of likelihoods.
it's weighted combination. It's weighted
And then
combination.
the weights are according
Weights
to
are the accuracy. Yeah, the weight is accuracy.
On the validation side or on the test side?
It's a okay. This in this experiment we evaluation and the training use the same the data.
Yeah. So because I mean these multiplication rules are very prone to overfitting, and if you put weights like these, so that might be a big problem, and that's why one of the reasons that you can be getting a diff over there.
Yeah, maybe.
So probably it might make sense to just try with like a
Mhm.
validation set.
So yeah, if we have the more data, it's better to divide it to the testing the how to say
So
the evaluation data and the
an
training data.
alternative to this product of HMMs and different HMM is just looking at the sum of likelihoods, which is much robust to noise. Because in multiplication, the fact that if one of the HMMs goes to 0, everything goes to 0. But if you're looking at sum, so basically that's a sort of a version of a. I mean, there's a tech report I can forward to you that says that in case of noisy scenario, you should use additions rather than multiplications.
Yeah. So yeah, this is a but how to say the robust estimate of the reliability of the different strings another open question. So right now we just use a simple accuracy. Yeah. So another the issue we explored is right now we use the very simple the combination. We just combine together actually the product of likelihood, or in other way the summation of log likelihood, and put the weight here. So it's a take risk. Sometimes it doesn't work well. But anyway, we tried another way. Is right now if we use the training scheme to build the combination, it's able to calibrate the output of the component output of the different components. So we use the different the training scale to build the combiner. We call it the train the combiner. So that's we tried the issue to improve the performance by to use the trained combiner. So in this case, we can see the output of the different modality as the input of a classifier, and the target class is how to say the output is a target class. So we use the different the training the training scale to build this trained combiner. So here is our experiment. The first is a unit string HM model, and then we use the fixed combiner. This is the weight is proportional to the accuracy, and then we use the different. Actually, we use the Gaussian combination and the Fisher combination to build the trained combiner. So in our experiment, the trained combiner is a little better than the fixed combiner because it's able to calibrate the output of the different modality.
So what's the difference between Fisher and the Gaussian?
So the fission, the Gaussian combination means we model each target classes by how to say based on we use the Gaussian distribution to model the target each target classes are modeled by the Gaussian distribution, and the feature the multi-fuse the HMM model. It's how to say we use the feature classifier.
So basically,
Mm-hmm.
yeah, basically, I mean, as far as I understand, correct me if I'm wrong, so you're taking the likeness of HMM and creating another classifier on top
Yes,
of it.
right.
And that classifier is using either a mixture of Gaussian or Fisher discriminant.
Yes, yes, yes.
Oh, okay. Good.
So okay, here I showed some the accuracy of the different emotions, especially with well look at. So in our experiment, the cognitive states, especially the frustration, interest, and the ball, have the worst performance. So we also notice the subject actually have the difficulty to express this kind of cognitive states by use the facial expression. It's very difficult. For example, if I ask you to express interest, how to express the frustration, how to express the ball. So it's very difficult. So actually, in this kind of situation, the audio is contributed more than the visual part.
This is again posed, right? It's not spontaneous.
It's a post. It's also a post. Even I ask you to post so interest, it's very difficult. So it's the audio part is more important in this kind of situation. So
measurement to measure the distance between different classes. So, for example, you say these three classes are difficult to differentiate. Do you have something, some measurement, some distance? Say, usually these two classes have much smaller measurements.
Oh, you mean the confusion matrix?
Yeah, some metrics.
Oh, yeah, yes, we have confusion, but I didn't show here. You can see the result in our paper. Yeah, you mean the confusion matrix? What kind of how to say it's what kind of the two the state are easily confused or not, right? So you can.
Who were the subjects when you counting data?
What?
What kind of who did you pick to perform those emotions in the data?
Oh, okay. This is a student and also faculty.
Bad actors?
Actually, they are not actor. So this is just a student in the university and the faculty or staff. They.
I'm a little bit confused because those emotions mean they're overlapped.
Yeah.
There's some overlaps. For example,
interested in
frustrated.
frustrated.
Yeah.
You can be frustrated and angry at the same time.
Can you be
It's not
happy?
exclusive.
Can you be happily frustrated?
Probably not. But you can be happy and interested. That's
Oh yeah. This is
Why there is a confusion matrix?
yeah.
But you train as one to many cloud, or you train multiple.
Oh, this is we just use we just how to say use the maximum the negative to be the criteria. So if the negative we if so.
So you have one classifier per category? Is that?
One classifier.
And there's multiple class problems.
Yes, but okay, we just choose the maximum and the negative. For example, if this model,
It's not like
you have
that.
you have 12 the model, right? Which model get the highest the negative? So we choose this one.
But you also have a trained classifier on top of HMMs, right? So that's a binary classifier then.
What do you mean?
I mean the combination, the one that you were talking about,
Mhm.
when you're combining, when you're training those weights,
Mhm.
using either Fisher discriminant or
Okay,
so
okay.
those are binary classifiers.
The minor classifier.
No,
Those
those
are-
are
those
those
are-
aren't.
I mean, how are you combining them when you're combining multiple HMMs using different weights, right?
Mm-hmm.
That's for single class.
That's a single class, right? So every class you have a
Yeah.
model
So
like that.
this is the how
That
is it
class chooses itself, yes.
generative model. So you just choose the one with the highest the likelihood, the higher the probability. So.
It's not a generative model anymore if you're combining the way as you were talking about
Mhm.
using Fisher discriminant or even mixture of Gaussians.
Mm-hmm.
So then probably choosing the model with the maximum likelihood doesn't make sense then.
Mm-hmm. Yeah, just choose the class with the highest probability. So this is a little summary about the multi-fuse HMN. So the bimodal can be outperformed individual stream, and the fused HMN is multi-fuse fused HMN outperform the multi-stream independent HMN. Trained combiner could be possible for the outperform the fixed combiner, and the most important feature is the brown movement in the video channel and the pitch energy in the audio channel.
I was just wondering what these sequences look like, what can sound like, and how long are they? And stuff.
It's a last from the 1 to say. I think the average the duration of the expression is about 1 second.
1 second?
2 seconds. 2 seconds.
Okay.
So,
And what does the audio sound like? I mean, so I can imagine facial expressions, I guess.
Okay.
What do they, you know, if they're angry, do they swear? Or, I mean,
what do they say?
Yeah.
Oh, yeah, yeah.
Say, or you just say what they
Okay. So, for example, the happy. Thank you, computer. You are very helpful, like this one. So it's a content that help the subject to pose this expression.
You just say different words, you know, from different expressions.
Yes, because if without the appropriate content, the subject is very difficult to express the.
Then if you run the recognition, then you will know which
From the words,
is.
right?
Yeah, from the words, they already know which state.
That's a good point.
You say, I'm frustrated. Of course, I know.
And also, and that for the audio signal or speech, they have something like laughing and or
No, nothing.
crying or something.
Okay.
Yeah, audio could be very biased.
So because in this scenario, it's because especially we wanted to induce the wanted to ask the subject to express the 11 affective states. It's very difficult if you have appropriate content. It's very difficult to express. So anyway, in our experiment, we just used the picture energy. So we didn't use the spoken word. So
Yeah. By the way, there are people. Actually, there are some data there. They actually ask an actor, professional actor, to say the same sentence with different emotions. Yeah, I mean, not normal people like us, we cannot do it.
Yes.
But the actor, good actor can do it.
yeah.
So I listen to
So
some
because
data.
the actor, they are trained to do this kind of thing, so they know how to express the difference between the expressions. But for the normal people, it's very difficult.
So that comes to my next question. How do you do normalization? Say different people, even for different emotions, some people express less, some people express more.
Okay. So because at the beginning, we ask the subject to express the neutral expression. So this neutral expression is a baseline for the recognition. So that means the mean of the pitch energy can be used as standard. So the other emotional expression, we just calculate the difference between them. So for example, like you said, the female and the male have a different pitch and energy. So we just use the neutral expression as the baseline.
So how about the visual features?
Visual feature, we also have we have the neutral phase. So we just calculate the difference between the neutral phase and.
But still, different people have different sort of extent to express, different expressiveness. Some people more expressive.
Yes.
Some people like raise the eyebrows more than some other people.
You're right.
So, like some people may sound may have same energy, no matter what is happy or sad, doesn't matter.
So
always speak a car, right?
Yes.
But some people they
someone more expressive, someone not. You're right. You're right. So this is my question is we use the neutral expression as the baseline. So even the face and the audio part. So next, the section I will talk about the multi-view facial expression analysis. So especially when I when when I moved to efforts from the pulse emotion to the spontaneous expression, we faced a lot of challenges. One challenge is how to say we must handle the arbitrary movement of a subject, because the spontaneous is you cannot ask the subject to how to say express the emotion in front of the camera, because most of the time the camera was hidden. So so this is a kind of arbitrary movement of subject. It's a challenge of the existing methods, which most of them are based on the front view facial expressions. So we build the system to handle the multi-view facial expression is the way to solve this problem. So the one question which I interested us the most is whether the non-frontal-view facial expression analysis can get the equal or the better performance than the front-view facial expression analysis. This is the question we want to explore. So here I did let me do a human perception experiment. I show a bunch of images, which is facial expression at a different the view angle. So here is so tell me what the view you think is the best for you to understand the facial expression. So here it's a profiled view of the facial expression, and then the subject expressed the 6 basic emotion. So it's in this the profile view. I think you will feel the difficulty to interpret the facial expression. Let me turn a little bit, so we get this angle view, and then turn a little bit, so you will feel much better, right? Because you get more and more the visual cue. So then this is the front view facial expression. So what's the best view? What's the best perspective for you to understand this facial expression?
Front.
So yeah, the most people will say, okay, the front view should be the best view for human to understand the facial expression, because that seems to they give you the most visual cue. So my problem is the front view is the best perspective for the machine to understand the facial expression. So we did experiment based on the 3D facial expression database, which was collected by Professor Yin at the Binghamton University. So the database includes 100 subjects with different races, and they asked the subject to express a neutral 6 basic emotions with 4 levels of intensity. And we use this database to generate the multi-view facial expression. We focus on right now is from the yaw rotation. We generate the 5 view angle from the front view to the profile view. In our experiment, we use the manual labeled facial points. So this is facial points. It's manual labeled. It's around the mouth, the eye, and the eyebrow. We use this the manual labeled the facial point as a feature, and we have 12,000 images, including the 100 subject, 6 emotion, the 4 level of intensity, and the 5 angle. So this is personally independent the emotion recognition performance. We use the 5-fold cross validation. This axis represented the different classifier. We use a different classifier, and from the LDC, QDC, and the Parson and SVM, and we use the KN and I applied the K in different subspace, the original PCA, LDA, LPP. And this axis represented the view angle. It includes the 0, 30 degree, 45 degree, and 60 degree, and 90 degree. So this is the accuracy. So in this experiment, you will notice the best view for the machine understanding is not the front view. Actually, it's a non-front view. You will notice, except this QDC, the best view is 60 degree. The classifier, we get the best performance is 45 degree. So, okay, this one is also the pattern is not 45 degree. But anyway, it's a non-front view.
This is because the way you pick features. Your features are not very good.
So the feature we use the we use the manual label the feature. So that's
no, I mean,
it's a ground truth.
When we see it, we see more than just those points.
Okay.
So I did a comparison a long time ago.
Mm-hmm.
So I compared the points with the Gabor wavelets. Features. Gaborism could give you much better results than points.
Oh really? Okay. Yeah.
So we see the subtle stuff, right? Not just that. Actually, it's not easy for us to see the motion of eyebrows. But it's much easier for us to see like the cheekbone margin. Very clear to us. I mean, we immediately perceive that. But when you fit the stuff in machines, you just roll on just points. You only give them points. If you just draw the points to us, it's hard for us to actually tell which one is better, right? It's hard for us to recognize expression. But once you presented the image here, we immediately see it because we got some other information in addition to those points.
That's good. Yeah, this is a possible explanation. So another. Let's see the. Here is how to say performance of different emotions based on the SPM classifier. This is the best classifier in our task. So we also get the best performance at the 45 degree. So the surprise and the happy are these states to recognize. The anger and the fear is it's most difficult to recognize. So anyway, so in this experiment, the result is struck us enormously because it's a different from our intuition. So because our intuition is how to say it's the front view shows the best view, but right now we get
45 is better.
I like 30. Yeah.
So yeah, so this is so anyway, this is interesting the result, and so yeah, like you said, in some way because the non-front view can give the depth of information about the face, and for the front view the depth is totally lost. So this is the possible explanation. But another the psychological explanation is I think it's in a human the face-to-face communication. Most of the time, we just use the display the front view of the facial expression, right? Because for example, when we're talking here, I give you my frontal face to you, right? Because I can eye contact with you, right? So that's very important. If I just turn around, so you cannot make sense. So you don't like look at me. You will look at the screen. So in our daily life, it seems the how to say the most imagery about the facial expression are the front of your face. So that lead to the how to say the human perception, the bias. So the people are more sensitive to the front of you, the facial expression of the face. So this is a possible the explanation from the psychological perspective. But in our experiment, we give the equal number of training sample for each views. So they evaluated in the failed platform. So the last work I will introduced is the spontaneous audiovisual expression analysis. So you may ask what is the difference between the post expression and the spontaneous expression. I show some video to you. So
thank you, computer. You have been very helpful.
okay. I will show another post discussed.
This background color looks awful. Give me a different color.
So when you watch this video, it's this is fake. That's totally fake because the subject how to say exaggerate his expression, right? But the spontaneous expression, this is the question to answer. Is
communicative. That's a word.
So you will see it's so different.
My dad, he wasn't really like that.
So you will notice the how to say the spontaneous expression is more subtle. It's more subtle, and they have the different the visual appearance and the different time profile, even the audio and the visual. So this is so different. So this is why the people right now shift the efforts from the post expression to the spontaneous expression. When we try to build the system, it can work in our daily life, we must face this challenge. Although spontaneous expression is very difficult, but we must face this challenge. So we did the preliminary the study in this direction. We used the data from the adult attachment interview, which was conducted in Professor Roisman at the UIUC. So in this scenario, the subject was required to describe the childhood, especially his the happy experience, the sad experience, or something. So it's the camera was hidden in the black glass. So although anyway, any subject that have signed the agreement, but they didn't know where was the camera. So that's so we can capture the real expression here. In our experiment, we choose the data of the two subjects, one male and another is female. The video lasts about 40 minutes. So the first the problem we have to face is if you try to build a system to recognize 6 basic emotions, you will be very disappointed, because you cannot get enough data for these basic emotions. Because the 6 basic emotions, happy, sad, fear, anger, and surprise is extreme expression. So in normal human-to-human communication, you cannot find the surprise, you cannot find the angry, the fear. So it's very difficult. So so most of the expressions are very subtle. So we turn out to So we turned to my efforts to build a system to recognize just the positive and the negative emotions. So this is it's totally different from the post expression analysis. And another question, another challenge we have to face is the labeling. So for the post expression, because you ask the people the happy, okay, this expression should be the happy, okay, but when you face this kind of spontaneous expression, so how to label them, even the agreement of the labeler, it's not so high. The labeling, the manual labeling of the spontaneous is full ambiguity. Fortunately,
the subject knows the mental state, right?
Oh, you mean the self-report?
Yeah.
Oh, self-report. This used in some of the psychology or the research. But if you try to ask them to self-report the label their expression frame by frame, second by second, it's most of the time it's not possible. Yeah, he can give most of the time. Just how to say when after the interview they will give the form, the generalized. So during this interview, what kind of expression did you have experienced? So that's okay. but you cannot ask them to label the second by second the expression. So it's not possible.
Yeah, so one of the things that we did while I was doing my PhD, so we were building, trying to figure out a system to recognize frustration in users. So imagine someone's interacting with the system and they have a button right there, I'm frustrated, quit. Basically, so the user themselves go and, so that's a positive point, that one positive point. But the way we went to analyze that data was that, all right, we have one positive point. For the rest of the data, we don't really know. So, but still, that's an information, right, that the user has explicitly provided. That's ground truth. And from that, you can kind of, sort of get some data about what his mental state was. But this has been one of the problems, and I think this field, right, how to get the ground truth. And in fact, like when I work with coders as well, even just trying to come up with a protocol that everyone would agree consistently on is itself a very challenging task. And unfortunately, not much actually work has been focused on just trying to get the label data so that you can build better and better systems.
So yeah, this is actually, there's some the method to get the labeling, especially I noticed that there's people who, use the video to induce some expression. For example, you watch a comedy movie, maybe that can induce the happy. But in this kind of situation, you just get the facial expression because this is not the interaction, the setting. So the subject was passive to watch the video and.
What about the movies? In the movie, where if you're angry,
the movie
that's
is
the most effective way, at least in psychology literature.
Yeah.
And that's one of the very sort of popular ways of eliciting emotions. But again, those studies are very hard to control for. I mean, the thing is, you can hope that those emotions will be elicited, but you can't guarantee.
Yeah.
Right. And but it's an effective way, and I think probably in computer science domain also, this should be probably one of the methods that we should be looking into.
Yeah, you just ask people to label some movies.
Yeah.
Yeah, this is so anyway, so the labeling is very challenging. So fortunately, we have the facial coding, facial action coding system, which was developed by the Paul Ekman, who developed this system to measure the visual appearance by the action units. So it's a kind of object description of the facial expression. But the problem is the audio part. Right now, so far, there's no this kind of the coding system to label the signal. So in our experiment, we make this kind of assumption: is a facial expression, a vocal expression, at the same the cause, the affective states, the positive and the negative emotion. So this is the assumption we made it in our experiment. Another is a segmentation. This problem is also very challenging because how to segment it for the automatic system. So we segmented this. Use the two criterion. One is the facial the expression is the intensity must be is higher than the threshold. Another is because the same problem, the arbitrary movement we cannot control. So we just segmented the video. It's almost a near front view, no occlusion. So this we must did some compromise to fit out the limitation of our technical. So the framework we used the two-stream, the hidden Markov model. For the visual part, we noticed because the facial expression is very subtle. So if we just use the 12 action unit, 12 motion units, it's not enough to capture this subtle expression. So we also use the 3D face tracker, but this time we warp the texture of the whole face. So use this the texture of the face as the feature. And then we used this is the high dimension. This is a warp the texture of the face, and then we used dimensional reduction methods, the PCA and LPP, to project the high dimensional imager to the low dimensional subspace and build the visual HMM. For the audio part, we use the porosity and then build the audio HMM. And then the fusion part, we try everything. So we tried just the fixed combiner and training combiner. Here we use the weighted combiner. And the last the combination is a trained combiner. We use the LDC, KNN, and AddBoost to try to every way to improve this performance of the spontaneous expression. So here is the experiment result. We do the personal dependent experiment because we have just two subjects. So we use the leave one sequence out cross validation. The first is the visual HMM in the PCA subspace. We get this experiment. You know even the subject have the different subject have the different the performance, because the different subject have the different the expression ability. And especially you all notice the male it's more expressive, or the female is more expressive, and we tried this is the visual HMM in the LPP subspace, and the worst part is audio. The audio HMM have the worst performance. This is reasonable because when I labeled the data, we didn't use the information about the audio. So another way is people also argued when we face the spontaneous expression, the porosity is not enough to calculate the expression. So we get the worst the performance of the audio HMM.
In your previous experiment, both pitch and energy outperform visual, right? A lot.
You mean?
You remember that you had the whole line of pose.
You mean? What's the question?
Yeah. How come we say this time audio is much less useful?
Oh, because okay. So for the spontaneous, there's this is two. I think there's a possible explanation. One is because spontaneous, but anyway, when label the data, we just use the facial action coding system to label the data. So that means the labeling we didn't use any information of the audio expression. Another is maybe the porosity is not enough. So it's.
You have only a few more minutes.
What?
You have only a few more minutes.
Okay, almost okay.
It's already 12 o'clock.
So we tried the fixed combiner. Actually, use the combiner is also in this kind of situation. It also take risk. It's even the female, the combiner, because the audio part is the performance so bad. So the combination is it's not helpful. And then we tried the trained combiner. So we see there's a lot of there's a different performance, even the trained combiner. So some worse, some better. So anyways, for this kind of spontaneous expression recognition, how to build the optimal diffusion model, it's very challenging. It's still need the further investigation. So let me summarize my talk. So in this talk, I first talk about the history of the affect recognition research. We indicate, I point out there's two trends here. One is multimodal affect recognition, another is the spontaneous expression analysis. And I talk about the multi-strain diffuse HMM, which is to make use of the correlation of the different strains. And we talk a multi-strain diffuse, multi-strain facial expression analysis, which is we explores the question whether the non-frontal-view facial expression can get the equal or the better performance than the frontal-view facial expression analysis. And then I introduced the preliminary result about the spontaneous expression analysis. So there's a lot of challenge here if we do some spontaneous expression research. Once the database, especially the labeling. For example, if you watch this imager, I ask you what is the affective state the subject expressed. Maybe the confusion, frustration, anything. Because you have no context. So this is why the reason the context is very important. What he's doing, what kind of environment he is. So it's very important. So for the visual-based analysis, we talk about especially how to build the system to handle the arbitrary movement of the subject. I need the further investigation. And the audio-based analysis, we need to integrate the linguistic and the paralinguistic the features. But anyway, how to get the robust to get this kind of feature? It's an open question, especially even the spoken words we cannot automate. So current speech recognition system cannot reliably to get the spoken words. So even for the some the linguistic some information is we can just infer from the semantic context, for example, the discourse information, but how to get it, it's very challenging. Another is how to build the optimum diffusion methods for this this problem. It's still largely unexplored. So another is context, when and what, where and why, and who. So, but anyway, although we faced a lot of a challenge in this research, there's still hope there. If we constrain our task for the specific domain, like detect the fatigue in the driving situation, detect maybe confusion in the learning environment, detect the frustration in the gaming system, maybe there is a hope because we have a lot of constraint, have good knowledge about the context. So this is a hope here. I'm optimistic about the future of this research. So I want to acknowledge my collaborators. They gave me a lot of support and encouragement to explore this complicated the problem. So if you are interested in this my work, you can visit my website and get the paper. Especially I strongly recommend a survey paper we did it recently. So that has been accepted in IEEE, the transaction and the pattern analysis and the machine intelligence. So you read the paper, you will get the whole picture about what happened in this field, what the challenger we have faced, what kind of database is available for your research. So this is the end of my talk. Thank you.
Thank you.